rings today in all biochemistry and all the chemistry. And one of the reasons that nature uses rings for a lot of things is because you compact a lot of information into a ring. But you can also compact a lot of energy into a ring. So I'm going to talk to you guys a little bit about that today. So we're going to talk about the ultimate goal of the project is synthesis of this molecule, or at least it was the ultimate goal. You know, there's lots of steps on the way, so it's kind of like we're having fun getting there and seeing what we can find. Because we made this molecule actually. So I'm going to talk to you guys a little bit why, what, how, where, and who we do this. So why tetrahedrane? Okay, tetrahedrane is a hydrocarbon and they burn really well. But it was not a known molecule because it does have a lot of ring strain. We've all talked about that in Orgo 1, those of you that have that. If you look in various literature places, it's predicted to be stable, but hasn't been made because it's not very easy to make. But the idea is if you put a lot of energy in, you're going to get a lot of energy out. Okay, so why, from a practical standpoint? Okay, well, you get a lot of energy out of it. Okay, we get some research funding from the Office of Naval Research, and one of the interests would be in making high energy fuels. One of the fuels that's used now is actually this one, JP10. You can see it's got a ring structure to it too. For just for your information, I don't know if anybody knows about the Navy has a cavitating torpedo. Will break the speed of sound underwater, but it doesn't go very far. I think how far actually I tried to find out. They told me this class. Anyway, you can calculate energy for various fuels using, here it's in megajoules per liter. You guys usually use kilojoules, most usually megajoules. So gasoline's about 35. You can do some rough calculations, and if you could make tetrahedrine, it'd be about 50. And for comparison, 25 megajoules, you could heat a bathtub from 60 to 100 degrees, so double that, or light a light bulb for 10 days. You have a liter of tetrahedrine, if it were liquid. We don't know. As far as the other reason we want to make it is just cool. Okay, tetrahedrine would be the last unknown of the platonic solid hydrocarbons, so tetrahedrine, cube, octahedron, dodecahedron, and icosahedron. These two actually are, you can make hydrocarbons that correspond to those. These you can't just because of the nature of the carbon atom. Okay, white phosphorus is actually tetrahedral, but it's not a hydrocarbon, so we really would like to do that. So it would look really and have a lot of energy, hopefully. Okay, we actually do sort of methodology development. So what we're doing is looking into how to make these strain ring systems, and if we could make that, that would be really great. So let's talk about how you do it on paper. Okay, one of the reactions that we're taking advantage of, which stems from my research going way back, has to do with the gamma-Seidel effect, which is sort of related to some of the chemistry we talked about in Orgo 2. We just started doing that recently in sort of SN1 type of chemistry, where when you have a leaving group come off, rather than having conjugation or hyperconjugation, you can actually have some stabilization of the carbocation center. By way of the back lobe here, and we'll talk about sp3 hybridized orbitals, they have this tiny back lobe that we usually ignore, which my research wouldn't be possible without. Okay? So the silicon is electropositive. It can donate electron density to the p orbital and help to stabilize the carbocation. And this is a strong enough interaction. The silicon will actually pop off and you can get a cyclopropane ring. This will go like that. And I'm showing it for a secondary ion here, which is sort of early research, and it doesn't work great. The yield is like, there's elimination and other things, and so maybe you get, 20% of this. But we found that if you put an electron withdrawing group here to destabilize the ion, it forces the silicon to donate more electrons. Okay? And for those of you who take Orgo 2, I told you that tertiary triplets are never stable, so there's an example where they are. But the CF3 kind of makes up for that. Okay, and it will bridge very nicely, and you can make trifluoromethyl cyclopropane with really good yield. And you might not think that that's particularly useful, but there are actually a lot of places where you see trifluoromethyl cyclopropanes in various pharmaceuticals, so make a bunch of those. Okay, you can see the relationship. Maybe we made one ring. Tetrahedrine is actually 4 cyclopropanes fused together, so there's a little bit of ways to go. But having said that, if you take the next step, which is actually to take a bicyclobutane and bridge that, cyclobutane and bridge that, you actually get what's called a bicyclobutane, and you can see it's pretty close. And we need one more bond. Okay, and this is a 4-membered ring. We actually found it works for a 6-membered ring and a 7-membered ring. Okay, 5-membered ring doesn't. If you want to know, you can ask me if you want. Okay, the next step would be, can we do it again? Okay, so that's sort of one thing we're thinking about. And it would be really cool. This would actually be a trifluoromethyl FEV ring. I don't know if you could do it without trifluoromethyl. So how do we do it not on paper? Because it never works. When you draw it on paper and try it in a lab form, most of the time it doesn't. You're research. So synthesis, glove box, step funnel. This doesn't look like it, but it's a 4-liter step funnel. Rotovap, purification, vacuum distillation, chromatography sometimes too. Characterization, NMR, GC mass spec. And we also do kinetics. I don't have a picture of my web that I'm doing kinetics. Okay, and you would also be doing reading and writing of literature. Okay, the research really involves organic synthesis, synthetic methodology, and physical organic chemistry, which is sort of, let's look at a reaction and see what it does and see if we can learn about it more. Studying reaction mechanisms, which I like to do, but I also like to do these other things. This is a great Sergey Prakash, who does a lot of fluorine stuff. And he's like made millions of dollars on some of the reagents and stuff he's made, so he can afford to say that. All right, so who and where? Okay, anybody who wants to, even if you don't wear pink on Wednesdays, can do this research. Okay, so this was my summer research group. You recognize some of the people here tonight, Becky, Alan, and Diana. This was Becky, who's actually visiting from UConn, and we collaborate with UConn too. And you don't have to work during the summer, you can work during the semester too. Mike Drago's working right now with me. Okay. And we have funding from the Office of Naval Research. Okay. We have collaborators with the University of Connecticut too. And there's a lot of people that have worked on this project over the years. I don't think I have them all listed. Okay, sort of the current people are the ones in pink here. Okay, and John is in green because he just started, so he's a green mark. So if you're interested, there's always plenty of room to work in the lab, and there's always going to be plenty of people that I'll need for this project. So what's next? Okay, what other electronic drawing groups can be used for bridging? What other ring systems can be bridged? Okay, and maybe we'll keep on going toward the tetrahedron. Maybe we could do a double bridging, or we can do one bridging and then couple it that way. And whatever else happens to come up along the way. We've gotten sidetracked before, and it's always fun. So. But I never like to get sidetracked, so with that I'll leave it. See if anybody has any questions.